So we need to talk now about Pythagorean triples or Pythagorean triangles. In other words, right triangles with integer sides. So let's say right triangles with integer sides. As an example, say I take this triangle that has one side is 3. It's not a good picture, but anyway, 3, 4, and 5. And they satisfy Pythagoras too. 5 squared is equal to 3 squared plus 4 squared. Now once we have an example, we can immediately produce infinitely many examples. We can multiply these numbers by something, by 10 for instance, and I get another triangle. It's just 10 times, all the sides are 10 times larger. 30, 40, 50. These two triangles are similar. So we have another Pythagorean triple. The basic 1, 3, 4, 5. And we say that this is a primitive triple or solutions where the three numbers are relatively prime. And this one that's not primitive is 30, 40, and 50. They still satisfy Pythagoras theorem. And then you can see easily that if one of them is so the general solution will look like this. It will be a primitive solution. Let's call it x, y, and z. That satisfy Pythagoras theorem. X squared plus y squared is equal to z squared. Z is the hypotenuse in this case. And then we can multiply this by any number we want, any integer number, because we talk about triangles with integer sides. Say multiply by d, and then it will become d times x, d times y, and d times z. And it will, of course, satisfy Pythagoras theorem. Because d times x squared plus d times y, so this is d times y squared, equals d times z squared. Because this is obtained from the other one just by multiplying the equation by d squared when we get it. Now, if two of them are relatively prime, two of these numbers x, y, z are relatively prime, then any two of them will be relatively prime. Or in other words, if two of them are divisible by the same number, by the same prime number, then the third one will also be. Say x and y are both divisible by 5. That's a multiple of 5, in fact of 25. That's a multiple of 25. The left side is going to be a multiple of 25. Z will have to be a multiple of 5. Or if x and z are both divisible by 5, that's a multiple of 5, that's a multiple of 5. Of course, the third one will be a multiple of 5. So y squared will be a multiple of 5. So y itself has to have 5 as a prime factor. So now we establish the following thing. Either any two of them are relatively prime, or if two of them are not relatively prime and they are divisible by the same prime, then the third one is also divisible by the same prime. So then it will look like this. D times x, d times y, d times z. So now, let's see. First of all, let me state the general result. It's very easy to state. I write it as a here. Let's say, and then we'll see other examples. So a theorem that gives us a way to find all of them. There are infinitely many, but something that will parameterize all the solutions. And the theorem can be stated as follows. So all the right triangles with integer size, all the right triangles with integer size are of the form of this form. Make a triangle, a right angle, and numbers like before. D times an x, same D times a y, same D times a z, where D is larger than or equal to 1, any positive integer. X, y, and z are given in terms of two other parameters as follows. A squared plus b squared, a squared minus b squared, and 2 times a.
2ab.
So, a squared minus b squared, 2 times a times b, and then a squared plus b squared. Where these numbers a and b satisfy additional constraints, 3 constraints. They are, say, a is strictly larger than b, and it has to be larger than b because x is the length. It cannot be equal. If a is equal to b, that's 0. It's not a triangle if one of the sides is 0. So a is strictly larger than b. B is larger than or equal to 1. B cannot be 0 because if b is 0, then y is 0. So again, one of the sides is 0. Then they are relatively prime. The greatest common divisor is 1. And exactly one of these two numbers is even. And exactly one is odd. So exactly one of AB is even. Exactly one of the numbers is even. This theorem, in fact, contains 2 theorems inside. A part of the theorem will give us all the primitive triangles. This part gives us all the primitive triangles, all the triangles of the form x, y, and z with the 3 numbers relatively prime, any 2 of them. X, y, the GCD is 1, x, z, the GCD is 1, and y, z. Y and z, GCD of those 2 is 1. This parameterization with these conditions will give us all the triangles, and it gives us each triangle exactly once. So that's why it's such a good parameterization. And then once I have all these triangles that are primitive triangles, I can just multiply each one of them by any number I want, and I get all the right triangles. D times x, d times y, d times z. Before I start to apply this in practice, then let's see why do I have these conditions. Well, if a and b are not relatively prime, if both numbers are, we saw why we need a strictly larger than b and b larger than or equal to 1, because otherwise we don't get a triangle, we get something degenerate. Why do I need a and b to be relatively prime? Well, if they are not, if both are divisible by the same number, like both are divisible by 7, then all these expressions are multiples of 7. So the numbers x, y, and z will be divisible by 7. So they don't form a primitive solution or a primitive triplet. So in order for this to have any chance, x, y, z, to satisfy these conditions, that they are relatively prime, A and B automatically had to be chosen to be relatively prime. But that's not enough. You cannot take both of them to be even, of course, because then they are not relatively prime. But we cannot take both of them to be odd. Although two odd numbers can be relatively prime. But what happens if I take A and B odd, both of them odd, and relatively prime? What happens is that these numbers A, B will be odd. Just think about what happens. Y is even because I have a factor of 2. X is going to be even because A and B are odd. So the difference of two odd numbers, when you square an odd number, you get an odd number. The difference will be even. And the sum of two odd numbers will be even. So then all three numbers will be even. So it is a solution, but it's not a primitive solution. All right. So if I forget about these conditions, and I remember only the equalities I have here, but if I take all the possible A and B numbers, I just work more, because I get the same solutions again and again and again. That's what I'm saying. If I use these restrictions, as I should, then I get each solution, each primitive right triangle with integer sides exactly once. Okay. Another thing, why does this work? Well, this is easy to see, this expression. So why does it work in the sense that why does this give always a right triangle? And of course, the numbers are integers, so with integer sides. Because it satisfies Pythagoras theorem. If I look at this, if I need to check x squared plus y squared equals z squared, well, in these expressions, a squared minus b squared, we can easily check that this one squared plus 2ab squared is equal to a squared plus b squared squared. So everything that I obtain here for any numbers A and B I choose, what I get satisfies Pythagoras theorem, and so a triangle is a right triangle. Well, let's check this identity. I have a difference of two numbers squared. Is the first one squared is a to the 4 minus 2 times the first times the second, so minus 2 times a squared times b squared plus the second one squared is b squared is b to the 4 plus 2ab squared is 4 times a squared times b squared, and this should equal this sum squared. The first one squared is a to the 4, 2 times the first times the second is 2a squared b squared, the second one squared is b to the 4. And indeed, I have an a to the 4 in here, and an a to the 4, they cancel, a b to the 4 cancels with the b to the 4. I have a minus 2 a squared b squared, but plus 4 a squared b squared gives me plus 2 a squared b squared, exactly what I have on that side. So it satisfies Pythagoras. So this always gives right triangles with integer sides. A more subtle reasoning is the following. How do I know that any triangle with integer sides is of this form? How do you prove such a thing? Well, first of all, you look at the triangle and you see if the three sides have or the three numbers have a common factor d, you write it like that. D times something, D times something. And then you're left with a primitive triangle. But the same question still remains. How do I know that when I'm left with a primitive triangle, x, y, z? I know that it's a right triangle, so I know that it satisfies Pythagoras theorem. And that by our assumption that it's primitive, I know that the greatest common divisors are 1, yz is 1, and xz is 1. How do I know that there exist numbers a and b satisfying these things and such that x, y, and z are given by these formulas? Because these formulas give me or give us already infinitely many solutions. But how do I know that there are other right triangles that are not obtained or obtainable in this form? So this requires some proof. Let me take just a few minutes to prove this. Then I suggest we stop the video and then we start another one where I actually use this parametrization to solve problems involving right triangles with integer sides. So here is still theory. How do I prove such a thing? This is not, so to speak, required for us to know. But for those who are interested in why does this work, let's see why it has to be of that form. Well, first of all, I claim that if I have an expression like this, they are relatively prime, okay. Exactly one of the numbers is even. Okay, let me see. You cannot have two numbers even, because if x and y are even, this is not 1. If x and z are even, this is not 1. Y and z are. Right. So, we cannot have two of them even. At most, one is even. But can I have 0 of them even? None of them, all of them odd? No, because an odd plus odd is not odd. Odd plus odd is even. So in conclusion, the conclusion is that one of them has to be even. We're going to denote that one by y. As soon as we show that the even one is not z. How do I show that the even one is not z? Well, if x is odd, y is odd, and z is the even one, then when I square it, it's a multiple of 4. So when I look at these numbers modulo 4, when I take any odd number, it's congruent modulo 4 to either to 1 or minus 1. Mod 4. So any number of x that's odd, it's congruent to 1 mod 4 or minus 1 mod 4, as we know. But when I square it, x squared, in both cases, it's going to be congruent to 1 mod 4. So x squared is congruent to 1 for the same reason y squared, y being odd. So x squared congruent to 1 mod 4, y squared is congruent to 1 mod 4. When I add these two numbers, I get that x squared plus y squared is congruent to 2 mod 4. But this is supposed to be equal to our number z squared. But z being even, when you square it, it's a multiple of 4. So z squared is not congruent to 2 mod 4, it's congruent to 0 mod 4. So we get a contradiction here. So in this case, x squared plus y squared cannot be equal to z squared. This shows that the even one, it's not z. So this whole part is only to help us deduce that one of them is even and is not z, and we'll denote that one by y. So that's why I can always put a factor of 2 here. I didn't show anything yet about a and b, but at least we know now that z is not even, z is odd. So what we know now is z is odd. Exactly one of x or y is even. Let's denote the even one by y. Even. And then x is odd. And I have, let me remove this part. And then I have x squared plus y squared is equal to z squared. X squared plus y squared is equal to z squared. I'm going to do the following thing. Right, y squared is equal to z squared minus x squared. And I factor this. So I have y squared is equal to z minus x times z plus x. Now, I know that y is a multiple of 2, it's even, so y squared is a multiple of 4. Both z and x are odd, z and x, so the difference z minus x is even, is divisible by 2, and z plus x is also divisible by 2. So what I can do now, I divide this equation by 4, and I write it in this form. Y over 2, this quantity squared, is equal to z minus x over 2 times z plus x over 2. And these numbers are integer numbers. We just saw that z plus x is even, z minus x is even, and y is even. So we can divide this like that. Okay, one more trick. These two numbers now are relatively prime. Z minus x over 2 and z plus x over 2. The greatest common divisor is 1. How do I show such a thing? Well, if they are not relatively prime, there is a prime number that divides both of them. If for some prime p, we have it p divides z minus x over 2, and p divides z plus x over 2, then both these numbers are divisible by p. Their sum is divisible by p. So p divides the sum. But the sum is z over 2, it's z minus x over 2 plus z plus x over 2. The sum, x cancels when you take the sum, and you get 2 times z over 2, then get exactly z. Now if I take the difference, z plus x over 2 minus z minus x over 2, the difference is exactly x. So p divides x. And we get a contradiction. So this is simply false. We assume that our numbers are relatively prime, x and z, x and y. So it does follow that these two numbers are relatively prime. Now, the next step, I have a product of two numbers. They are relatively prime, and the product is a square. Now, if I have two numbers that are relatively prime, and the product is a square, I claim that each one of them is a square. Why? Think about the prime factorization of the first number. Think about any prime factor, p. We just saw that, I don't know what the exponent of p is in the first number, but definitely the p does not appear in the second one. We just saw that they are relatively prime. So p appears with a certain exponent in the first number, 0 exponent in the second, no p in the second, but the numbers are equal. So p has to appear on the left side with exactly the same exponent as on the right side. But on the left side, we have a square, so the exponent of any prime number is an even number. This forces the exponent of our p in the first number to be even. And this holds true for any single prime factor of this number. So this number has the property that all its prime factors appear with an even exponent. So it means that this number is a square. And the same for this one. Any prime that divides z plus x over 2 will appear with an even exponent in the number because it cannot appear here, and it appears with an even exponent on the left side. Okay, and we are basically done. So now I know that z plus x over 2 is some square. Z minus x over 2 is a square. So let's denote this somehow. The square of some number, let's call that little a. So z plus x over 2 is the square of a number, a. So it's a squared. And z minus x over 2 is the square of another number, let's call it b. So it's the square of a number, so it's b squared. Oh, so I got my a and b. I hope I got them right. So now I just solve this. I can find z and x in terms of a and b. And we know we already did it earlier because we need it. So I add these two equalities. I add the two equalities. On the left side, I get z plus x over 2 plus z minus x over 2 is z. And it equal to a squared plus b squared. And when I take the difference of these two numbers, the difference is actually x. So z cancels and I have x over 2 minus x over 2 is x. It's the difference. So it's a squared minus b squared. So I got both z as I wanted, a squared plus b squared, and x, a squared minus b squared. Lastly, we get y. Where do I get this y? From here. Because this number was denoted by a squared, and this number was denoted by b squared, by us. So, so this simply means that y over 2, this quantity squared, is equal to a squared b squared. So I multiply by 4 and I get y squared equals 4 a squared b squared. So y is 2ab as claimed to be there. This is a proof that all the right triangles with integer size have this form. And then the rest we saw earlier. That once it is of this form, if the numbers are indeed relatively prime, if this is a primitive solution, then the A and B have to be co-prime. Exactly one of them is even and exactly one of them is odd. So because otherwise, if you have odd, then everything becomes even, and so on. And A, of course, strictly larger than B, larger than or equal to 1. Strict inequality, because if A equals B, this becomes 0, and if B is 0 instead of being 1, then this is 0. Okay, we can stop now and then we work on some problems.